Well, hello everyone. Welcome to this new episode of Forecast. I'm your host Tim.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel and you can ask us questions there. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask questions on the channel during the episode. So without further ado, let's get to it. So Tim, I remember we had a previous episode about space-time being doomed. For all of you watching this or watching this in the future, do check that out. That's a very highly interested topic of high interest to many people. And now we're talking about particles being doomed. Before we go into that, I want to start off by asking like, what is a particle? When most people think about particles, they think of like particles of dust or maybe like, the fun of like electrons, protons. Like, how do you think about a particle? Like, what is it?
Yeah, so a particle in particle physics or physics in general, it's a type of constituent, a unit of things happening, and very intuitively, you can study in the lab. You can isolate like a proton and study a property, and every time you study a proton, it will have the same property. So a particle can be loosely thought of as some kind of consistent unit. I mean, going all the way back to Aristotle, like people thought atoms were kind of the smallest unit. Of course, now we know atoms are made up of the nucleus and electrons. The nucleus is made of protons and electrons. The nucleus is made of protons and neutrons. So a particle, in its broadest definition, is kind of a unit that has some consistent properties, like mass, for example. They could have charge. Like it would be disastrous, for example, if one proton has some kind of charge and another proton has a different kind of charge, right? That would be disastrous for the world, right? We wouldn't have consistent chemistry, right? So that's what a particle is the highest level. It's just some consistent unit of interaction that we can kind of that's pretty reliable, right? And that's how we talk about it. It's kind of like a unit of talking about physics.
I see. So I want to get into a little bit of the taxonomy of it, just to clarify definitions, then we can get to other things. So, like for instance, a proton and neutron are made up of quarks, or at least on average, are made up of quarks. Are protons and neutrons like particles, or would you consider the quarks inside of them to be particles, or are they both particles? Like, how do you think about that?
Yeah, I think they are both particles. And this is the right way to think about it. Particles have some kind of a scale. Of course, if you zoom out, compared to the humans, proton is very much an individual particle because you cannot see the constituents of it. And in the same way, atoms are kind of like a particle. So you could write down physical laws treating atoms as the individual particles, and that's what is done for like protein folding, for example. Look at each atoms individually, right? So they are both particles. And of course, in this reductionist point of view, particles can be made of other particles. And you can kind of go down and down and down. And the belief is that when you go down to the smallest constituents, the indivisible constituent, like Aristotle said, they thought atoms were indivisible. But the smallest indivisible ones are what I call the fundamental particles, right? These are the things that cannot be broken more, right? Um,
Mhm.
Yeah, so I think your intuition is correct. They are both particles.
Gotcha. What would stop me from calling you a particle then? Because it seems like you're going at different scales. Like, what
Yeah,
makes
like
you not?
look, if you look at the galactic scale, imagine you're zooming out looking at galaxies. I would be nothing but like a speck of dust, right? So from that scale, it's totally fine for you to call me a little particle. Obviously, I'm stuck on Earth. In fact, you would probably call Earth a tiny little particle, right? Imagine they're galactic beings, which they aren't, but if they were to exist, yeah, you can very well call them particles. And if the galactic beings didn't have like some kind of microscope or like UFOs or whatever in their disposal, the Earth, the Sun, or even galaxies could be thought of as particles. So in some ways, that's not totally crazy. But in this reductionist view, right? Like the fundamental particles are the ones that are truly indivisible, right? Assuming that they exist, then
Mhm.
those would be like the most, how do I put this, the littlest unit, if you call it that.
I see. I see. So I guess like a particle, it seems to me a particle, the way it's defined is like what is most useful. Like in the context, if you're looking at a galactic scale, you consider an Earth to be a particle because it's so small. But if you were like to look at us and we viewing the Earth, we probably would not call the Earth like a particle because it's larger than us. And like it's not, I don't know how useful it is to think like in everyday life here, not going to the cosmos, whether or not that's a particle.
Yeah, I mean, utility certainly is a part of it, but I think it's hard to deny that there's also um, that there's also experimental evidence, right? Like you could theoretically use like electrons and quarks and gluons as your fundamental particles as a description for the cosmos. You could do that, but not the other way around. Like you couldn't treat the Earth as a particle and then think about particle physics. That would just be wrong, right? So there is like this one way direction. The smallest particles seems to be kind of more valid in that way. So in that sense, yeah, it's a bit of a utility, but there's also like some sort of truth behind it. Like you can experimentally go in and grab a particle for me every time, and it seems to be super darn consistent. So why not, think that they really do exist?
So is it the more consistent the unit is, the more of a particle it is? Would that be fair to say?
Yeah, I think that's absolutely fair to say. Like the definition of a particle only exists to the extent that is consistent, right? Like if I grab a proton now and I grab a proton later, if the properties are totally different, then I don't know if I would call that like a particle of proton, right? That would be kind of crazy, right? But then here's the question now, like how consistent are these particles, right?
Yeah, I was gonna ask you, like, say we look at charge of like an electron, for instance. If you do experimental measurements of charge, you'll probably get different results each time. So then how do you know that it's like consistent? Like, what does it mean to be consistent?
Well, there's something to be said about error that are reducible and error that are irreducible. And of
Mhm.
course, similar to the previous episode, this distinction is super important. So far we have not seen irreducible error in the charge of the electron. Although mm, up to slight debate, it's quite technical, but kind of so far. I mean, quantifiers, right? This is where we're getting into. So the charge, yeah, it's pretty much there isn't an irreducible error. But like you mentioned, yeah, some properties actually are reducible. There are irreducible errors.
Before we get into that, can you define for the audience what is a reducible error and what does an irreducible error mean?
Yeah, like an error that's reducible, it just means that you haven't tried hard enough, right? Like your experiments are either too crappy or not precise enough. So if you try hard again, you'll get a better measurement. But certain things, no matter how hard you try, you just couldn't get there. Maybe these are kind of like stories of life for a particle.
I see. Okay. So I guess is it possible to tell what is a reducible and what is irreducible, or like kind of going into the philosophy of that? We're just slightly going off tangent, but I'm curious, like, I mean, how do you know certain errors are irreducible? What do you just try really, really hard? Like the
Yeah,
hardest possible.
when something is irreducible, it's both things. You can, like, if something has an irreducible error, uh, first to confirm it, you can try to measure it to see if there's really some error that just never can be teased out. Well, of course, you can blame it on your equipment. Your equipment just sucks. I don't know. Maybe you got some faulty stuff from Amazon that just doesn't work very well. Fine, right? But sometimes, when errors are irreducible, you can quantify them. We have theoretical models to see how irreducible they are. So it's like even though they are errors, we have models that quantify those errors. And if those two match up, we know we have an irreducible error. But how do we know when something isn't irreducible? Well, we will never know because measurement always have some error. You can have, maybe in the theory you think, oh, there's no irreducible error, but who knows, right? So to prove that it's irreducible, well, wait, let me get this straight. To prove that it's irreducible, it's quite straightforward. If you have a theory that says there's some error that you just cannot get rid of, and you do indeed measure it, lo and behold, yes, there's irreducible error. But to show that there isn't, that's tough, right?
Okay, that makes sense. So coming back to our discussion about certain properties of particles, we were originally talking about charge. What other properties of particles that are like consistent, but you said may not be so consistent?
Yeah, and in fact, when I was mentioning charge, like with a caveat, charge turns out to be not totally consistent. And
Oh,
it turns out to be true, even, well, okay, let's look at some of the more common variable to measure. One of them is mass, how heavy a particle is, Um, as far as, well, actually, also with some caveat. Like some particles, it depends on the particles you're talking about. For electrons, we believe the the mass is kind of the mass has no error, kind of, because it's
mhm.
stable, right? And and but then how do I put this? So it depends on particles. So charge is kind of doesn't have a lot of error. The mass depends on the type of particles. Some
Mhm.
particles, their mass can have a lot of errors, and some have very little error, right?
Mhm.
And also things like more sophisticated variables like spin has to do with quantum mechanics, which we will not go into, and other types of charges, maybe the charge under the strong force, the charge under the weak force, things of that nature. So these are kind of the broad properties of particles.
I see. So there are these broad properties of particles, charge for most part with some like asterisks, little footnotes saying that it's not consistent in these edge cases, but for the most part it's consistent. Mass of more stable particles like electrons are more consistent. What about like particles like neutron that apparently if you leave them by themselves they decay like 12, 15 minutes? Like is the mass of that consistent or
Yeah, that is a very good example. When things decay, it turns out their mass is not consistent. Because when they
hmm,
decay, so here's a question. Like how do you measure the mass of something? Right? In order to measure the mass of something, you kind of have to interact with that particle. So this comes back to one of the core principles in quantum physics is that to measure something, you kind of have to disturb that system, right? And the more you disturb that system, the more you kind of mess it up, right? So you kind of mess up your measurement. So how do you really do the perfect measurement, right? Basically, you have an apparatus that kind of really gently just kind of interact with the particle, very as gently as possible, and for as long of a time as possible, right? But for neutron, that's not possible because after a while they will just decay. so your so from that angle, um, neutron neutron's mass has what we call a mass width, meaning that if you do a measurement of the mass of neutron every time, no matter what you do, there's some error band, right?
mhm.
So and if you look at other particles that are unstable, that are maybe the audience are less familiar with, like the pions or the Higgs boson, even, the more unstable they are, the more error there is. The mass is less and less well defined.
I see. I see. I was gonna ask you something about that. So regarding for the actually, yeah, so let me in fact like go to even a more like one level lower type of question. How do you even know that a particle is there to begin with? Like how do we know they actually exist or like are there? Like what does that mean?
Once again, that's a fantastic question. You know, like look at our everyday life. How do we know the table exists? Because we touch
Mhm.
it, right? You can say we have some interaction. And in terms of particle physics, touching involves very little energy. Like, right? I mean, you eat your dinner, you just touch the table. I mean, that's not a workout, right? You can tell. So it's a very low energy interaction. So this kind of existence is what we call kind of low energy interactions. And you also you take a long time to feel this table, right? So in some
Mhm.
ways, the table's existence has some uncertainty. But of course, the uncertainty is so small, it's quantum mechanical. So we don't think of it very much, right?
Mhm.
But come on, we're talking about fundamental physics here. We're talking about absolute existence. And does that make sense? right? Is it always true that no matter how I touch the table, how if I tap it lightly versus I smash it like a hammer, is it still gonna feel like a table? I mean, that's the question, right? Like if it's not true, I don't know if the table is really there in some ways.
So you're telling me like if I have the table in front of me and I like just smash it, like just go to town on it, and then I won't know whether it's actually there because I probed it with so much energy that it like no
Well,
longer
well,
exists.
yeah.
Okay.
I mean, Sahil. I mean, no offense for humans, right? No matter how hard you try, your energy output is gonna be pretty minuscule. I don't care if you're super muscular, you're like the world bodybuilding champion. That's not happening, right? But um, we're talking about cosmic levels of energy, right? Like,
Mhm.
just imagine, like, me touching the table and whacking it with a camera, pretty much the same amount of energy, minuscule, right? I'm talking about hitting the table at the speed of light. I mean, I can't do that with my hand, but if I do
Oh.
that close to the speed of light, I'm gonna start like a nuclear reaction. Like the town is gonna go kaboom, right? And even more energy. If I shoot enough energy at it, it's gonna make a black hole, right? So for us low energy friends, like it's pretty
Mhm.
clear that the table exists. But imagine our, I don't know, aliens or whatever, alternative particles, a warlord, whatever, right? These are imagine they're these cosmic beings with super high energy. They'll be like, yeah, I'm not so sure about your table because when we blast them, we just saw a black hole, right? Where's the table?
Hmm.
Now that, in some sense, very similar to the reason why space time is not precise, and in the same way, you know, the existence of things is also not very precise.
Huh. So are you saying that the existence of things depends on like the energy at which you probe them at? Like for us low energy beings, we perceive things are there because we can't like generate so much energy to like create black holes or like yeah, like how does that relate to this point of like
Yeah,
existence?
that's absolutely spot on. And this is in fact something we see, we study, we verify in
Mhm.
particle physics colliders, right? So in our everyday life, like I said, the energy is very low, so the existence of everything we see on Earth is very consistent, right? I see a table, you come over, touch the table is there, no question, right? But if you look at the particles in a particle accelerator, let's say you have a beam of protons, and you were sure you put protons in, right? Like, the experimentalists really carefully took all the hydrogen, strip off the electrons, and these are legit protons, right? Accelerated up. And now you imagine you collide one proton with another proton. And when you collide them at really high energy, we see that what one of the protons sees, it's not necessarily a proton. This proton, because it has so much energy, we can kind of visualize it as it has so much energy that it creates kind of a cloud of all of the other particles. Sometimes when the protons come in, it might see the proton with good probability, but it might
Mhm.
see things like a quark or gluon, the constituents of a proton. It might even see like things like strange quarks that might not be that they're typically not thought of as being in a proton. It might even see a gauge boson, W and Z's. It might even see a Higgs boson. So we see that, and in order to study the interactions of these particles, we have to take that fuzziness into account. That's the only way to get it right. So in this sense, we have proof that the existence of particles has an irreducible error. Like that's indisputable.
Hmm. So can we like describe to the audience if you like I mean let's take the example where you have like a proton that's just like just chilling by itself, minding its own business, and then you come along with like a really really powerful detector, not so powerful that it turns into a black hole if you interact with it, but like just powerful enough to be below that limit, like just enough, and I interact with it. What would happen? Like where do all these particles come from as you were describing? Or like what would happen, or what is this cloud that you speak of?
Yeah, so all that comes from just interaction, right?
Mm,
So in some sense, particles are only well defined when you strip off all of their interactions. which is
Mm-hmm.
impossible if you think of it this way. But it's kind of like a thought experiment. If we strip away all the interactions, then a proton is a proton. But yeah, when you hit it with that much energy, you
Mm-hmm.
know, you have to study all the possibility, all the quantum mechanical possibilities, and when you have
Mm-hmm.
that much energy available, the protons can easily split into other particles. It can split into, I mean, if you put in enough energy, kind of below just below the threshold to make a black hole, ooh, hell's break loose. This is quantum gravity regime. I don't know what crazy stuff will get created. Strings, extra dimension, you name it. There could be weird stuff coming out. I would have no clue actually. I'll be very excited, obviously.
Fair, fair. Okay, so then, okay, so if you were to like interact with it at a very, very high energy, just enough before it turns into a black hole, then it's and you look at it at that moment in time, whatever that moment in time even means to for starters, then you would see like a whole bunch of particles, and you may not even know if there was a proton to begin with. Is that
Yeah,
fair?
exactly.
Ah,
For all
so
we know, you could have snuck something else in there, and you didn't give me a proton. For all we know, yeah.
I see. So are you saying at some level that particles become indistinguishable at higher and higher energies?
That in some sense is true because when you go at higher and higher energy, the
Hmm.
many different modes become more active because so what are these modes you speak of? So in particle physics, the laws of physics are governed by what we call fields, kind of like water, whatever, some abstract substance, but not quite substance, right? And particles are
Hmm.
just little jiggling excitations of it, right? And the mass of this particle is just like a gap, like something that's preventing you from jiggling those fields, right? Um, it's like the minimum required energy for you to mess with it, basically. I mean, it's like the table, like how hard do you have to whack it for it to break? There's some threshold you gotta go through, right? And these fields are similar. These different modes, you kind of have to whack it hard enough for it to create something meaningful, right? So at higher and higher energy, then at some point, all these modes are possible. You've excited them all through gravity, because gravity is the king of all particles. It sees everything. Everything that has energy, not just mass, that has a gravitational field, right?
Hmm.
So it's the universal detector almost, right? So yeah, when you send enough energy, all these modes are kind of coming alive basically, and
Hmm.
the interactions become more and more universal, right?
Mm, that makes sense. And I guess like in the absolute limit where you reach that like maximal energy threshold or whatever, and you turn everything to black holes and like there's no telling what it is. Everything is the same basically.
Yeah, exactly. And let me add an extra point, right? Like you might think that, oh, dude, that's so artificial. We're never gonna have a hammer that powerful. I don't care if you're like superheroes, right? Like Superman or Wonder Woman or Thor, right? Okay, that's so artificial. Well, it turns out that it's not. Even if you don't want to make black holes, the universe makes it for you, right? Um,
Mm.
what do I mean by that? So look at the universe right now. Give or take 10 billion years. What's going to happen in the far future? And by far, I don't mean another 10 billion years. I mean trillions and trillions and trillions of years, right? In some sense, our lifespan in the universe is very short right now. It's nothing, right? And ultimately,
Mm.
one day, probably, all the matters that exist in the world will just coalesce. Stars will collide, black holes will merge, and ultimately, at the end of the day, we'll just end up with one massive black holes and just sucking everything up. And at the end of the very 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 end, even black holes will decay, right?
Mhm.
So at the very end, like the end game, right? If you imagine you're playing a game, this is like 1,000 hours in, uh, you just end up with just nothing. Like black holes swallow everything. You get particles of light, but these light will just get stretched out, redshifted. They have lower and lower energy. They might as well just not exist. So it's just like totally void, right?
Can we describe what redshifted means? Like it would it be like you can imagine as if like kind of these like photons are like these waves in this box that we call the universe,
Mm.
and as the box grows bigger, the waves like get like thinner and thinner because you're stretching it longer and longer, and so eventually it just flatlines as nothing. Is that an apt analogy for that?
Yeah, I think so. It's kind of like cheese right, on a pizza. You stretch it out, the cheese gets thinner and thinner, thinner. There's like less and less cheese, I guess, per area. And like in the same way, like the amount of energy for a particle of light, it gets less and less and less until it just gets diluted to nothing, right?
Hmm. Okay. So then eventually like there's like nothing in some sense. So in other words, these particles don't live forever.
Yes, that's that is kind of a bit of a shocking thing, but maybe not that shocking. If you think of the entire universe as a massive experiment, right? You know, the universe gets created, particles get created, we bump into each other, then humans form, and Sahil, you and I are chit chatting. One of these days, galaxy goes away, black holes, and all that. At the very, you kind of started with nothing, right? You know, maybe some
Mhm.
vacuum energy, blah blah blah. And at the end of the day, you also end up with pretty much nothing, just black holes and decay, and nothing's left. So in that sense, yeah, nothing really lasts forever, right? Even
Mm,
particles that we think are sacred or like are completely stable that have some persistent properties, right? Because the lifetime is not infinite. That means there's always some irreducible error for everything you measure, right? So
I see. I see. So I guess the diamond company should have consulted you when they said diamonds are forever.
right, yeah. I mean, diamonds are kind of a low bar. Diamonds are already metastable, but maybe maybe we can start like a lawsuit. Diamonds are forever. Think again. But yeah, but even protons are not forever. They'll probably decay, but even electrons are not forever. Uh, Maybe particles of light, you can think of them as kind of forever, but they do get diluted to nothing at the end.
Mm.
So at the end, everything is doomed in some sense.
I guess like coming back to I want to kind of quickly spend time a little bit on like
Mm-hmm.
the human mind consciousness aspect. So from like our perspective, it seems like the the description of particles are things that are distinguishable. Like if you talk about things at higher energy where everything's the same, then the notion of a particle may not make as much sense. Like if everything is like near this limit where everything, or imagine there were just nothing but black holes, it would not make much sense to distinguish between different particles because you couldn't. But from our like lower energy perspective, we can tell the difference between different things. So I'm wondering, like, if you were to, I know this is such a difficult question and there may not be an answer to it, but if you were to like try your best to step outside of ourselves and view it from the perspective of the universe, are there really particles? Because there's like, it just seems like all there just is, like, it's just one thing, or not one thing, but just, I don't know what to even call it.
Yeah, and I would say uh, the answer probably is that there are no real particles. I mean, that's the real kicker. Particles ultimately are just a convenient tool for us to study these mathematical objects, right?
Mm.
And we define them even theoretically as kind of this approximate construct where if you remove all the interactions, then you get these idealizations. So in some sense, sadly, yeah, um, it feels like nature it got a better hold of us, right? So it's more nature is more intricate. I think we try to approximate it, but if you think real deep, it still falls short to some extent, right? So yeah,
Mm.
I would say that question, uh, particles are probably not ultimately well defined, but they are well defined now for our limited existence in this universe.
Ah, I see. That makes sense. I guess like then I guess one other question I wanted to ask is from the perspective of uh if you were to like go like early in the universe where everything was like really hot and very dense, um like would you be able to count things, or would like it just be like one, like, I don't know, blob of plasma, or what would it be like? How would you think about it as you go to like higher and higher energies?
Yeah, I mean, in the early universe, I think the concept of particles are very different. And once again, the concept of particles only exists to the extent that it's convenient for us to think about things, right? And if we were living, imagine we could survive, humans could survive in this super hot plasma and not just totally melt away, right?
Mhm.
We're not gonna feel the ambient very much. We're just gonna be like, ah, it's just like a hot bath. I'm just comfy, whatever, right? Like you're not gonna notice it very much. Then the definition of a particle will be the extra energy on top of this hot plasma. So
Mhm.
all the particles that we know and love, things like electrons, particles of light, they will they will look different. They will become dressed by this plasma. It's almost like imagine these particles. Imagine someone very famous going to like a party, right? This is kind of an analogy. Everyone just crowd around, and you don't really just see the person. You kind of see like a whole aura of the person, right? So
Yeah.
that's what it'll be like, right? But at the same time, if you think that notion of a particle doesn't make a lot of sense, to some extent, it still applies in the modern day, even when temperature is not as hot. There's always this effect of an aura around the particle, and this is a result of all the things we said, right? Particles
Mhm.
have interactions. They don't live forever. They
Mhm.
minimally they have gravity, and all of this makes it so such that the identity of a particle is fuzzy, very fuzzy.
Gotcha, gotcha. So then, last question I want to ask before we leave off, and just I just want to I don't spend like too much time going in depth. I just want to describe it at a high level. So I don't think we even need to look at higher energies for like newer particles and whatnot. Even like within materials like low energy, you can find, I think, what we've referred to in the past known as quasi particles. Could you describe that notion that if you change the substrate that you're based in, like the environment that you're based in, like new particles can form and how we create those?
Yeah, so this notion of quasi particle is highly relevant in materials research. Breakthroughs, there are many breakthroughs studying them. So when people imagine kind of these mini mock universes, when you have, let's say, a hunk of metal, you have these lattice structure of atoms, and you imagine the life of an electron. When you're living in that lattice, you kind of just, like I was saying before, at high temperature, you when you're in it, you kind of just feel the ambient substrate. You don't feel very much of it, and and the particles that are useful to talk about here are the excitation on top of the substrate, right? So this is the view that material researchers use to study things like transistors, superconductors, and whatnot. Uh, and but of course we know that from the reductionist point of view that this will break down as long as you just grab a hammer and smash the piece of metal and then all the lattice broke apart. Let's say, then it becomes invalid. But still, this flavor of um, particle being dressed up by their substrate, like particle with an aura, the way I put it, is still very much valid. And this carries over in all kinds of situations in a material, in a hot plasma, or just particles themselves.
That makes sense. So we're basically at time. I want to give you a chance if you want to leave the audience with anything that take away from this episode.
Yeah. So I don't know. Maybe the title is a little too much gloom. We're saying particles are doomed. It's true. Nothing lives forever. Of course, particles will outlive many of us, but ultimately they are also not permanent. But maybe in some sense we should kind of flip around, right? Um, it, like it's not such a bad thing that all the interesting physics that we see are kind of not permanent, right? I don't know. Maybe this is kind of like a Buddhist esque sort of feeling, right? It just tells you that look, like live your life, like all the material that is there, they're not gonna last forever, right? And the fact that they're real is just because we exist to examine them in this fashion. So kind of, I would say just maybe there's some life lesson there. Treasure the universe around you. it's enjoy it while it lasts. So let's put it that way.
That's fair. That's fair. I think that's an excellent life lesson. So on that note, I want to thank you for joining us, and we'll see you next week.